Nu avem niciun semn. Atunci să vedem Octavia-Maria Hapenciuc de la Universitatea din Brașov, Universitatea Transilvania. Mergem mai departe să vedem atunci pe cine avem prezent. Timea Melinda, se poate? Suntem auziți? Chiar nimeni? Așa, vă rugăm, da, sigur.
Bine. Ziua, da, la mine s-a întrerupt un pic, mă scuzați. M-ați strigat cumva Octavia Hapenciuc de la Universitatea Transilvania din Brașov?
Dacă se poate, da, conform grilei dumneavoastră ați fi. Acum să vedem. Da? Doriți acum dumneavoastră?
Sigur.
Bine, și atunci după Octavia-Maria va veni Timea Melinda. Bine?
Da.
Ok. Bun, vă ascultăm. Eventual să doamna Hapenciuc să încărcați prezentarea.
Da, imediat. Se vede?
Da, se vede, vă ascultăm.
Prezentarea mea va fi în limba engleză. Hello everyone, my name is Octavia-Maria Hapenciuc and I'm a master's student at Transilvania University of Brașov. Together with my coordinator, Professor Dr. Marin, we researched the study of eigenvalues of Sturm-Liouville problems under perturbations. This is the chapters that we will go through with this presentation. And we introduced a regular Sturm-Liouville problem given by the equation 1.1, where P, Q, and R are integrable functions on the complex plane. And the problem is considered together with the boundary conditions given in the matrix form given by the relation 1.3. In order to characterize the eigenvalues, we need two matrices, P and R, given by the relation 2.1. And we also consider a matrix solution phi of the initial value problem in the equation 2.2. For this, we need to define a characteristic function delta, given by the relation 3.3. And considering what we stated before, the characteristic function is well defined and continuous for A and B, for fixed matrices P and R and fixed lambda, and also it's an entire function of lambda. Considering the relations that we stated before, a complex number lambda is an eigenvalue of the problem with the boundary conditions 1.1, 1.2, and 1.3, if and only if delta of lambda is 0. And from this, we obtained four cases of these eigenvalues. Either there are no complex eigenvalues, every complex eigenvalue is, every complex number is an eigenvalue, there is a finite non-zero complex eigenvalues, or there is an infinite but countable number of eigenvalues. In order to simplify the study, we considered two types of boundary conditions, separated boundary conditions and coupled boundary conditions. And we gave the lemma only for the separated boundary conditions. The other one will be respectively demonstrated. And we consider the matrices, we fix the matrices A and B given by the relation 2.4. So delta of lambda will have this form. In order to give an example of how the solutions modify when we modify the boundary conditions, we consider the time-dependent wave equation for a vibrating violin string. We know that the vertical displacement of a violin string of length pi satisfies the wave equation. Also, the ends of the string are fixed. The string is plugged in the middle from the resting point. And we need the function to satisfy these initial conditions. We solved the equations and we found these solutions for the equation. And we generalized the problem by modifying the boundary conditions in this matrix form. And for coupled boundary conditions, we got this delta function. And we considered different cases. In case 1, we have C equals minus D, and in this case, the delta function is a constant independent of lambda. And of course, if this constant is 0, then every complex number is an eigenvalue, and if it's not 0, then no complex number is an eigenvalue. In the other case, in 2, here, we consider that C is different from minus D. So the characteristic equation is given by this relation. The roots of the equation are these, and we studied 2 different cases. When C equals D equals I, we have these eigenvalues, and when C equals minus 1 equals D, we have the self-adjoint periodic case, and these are the eigenvalues. For further study, we need to introduce the space of regular boundary value problems. This is given by the relation 3.1. The only difference here is we have to notice is that the functions P, Q, and R are locally integrable on the interval J. By eigenvalue of omega, we mean an eigenvalue of the boundary value problem determined by omega. And we want to show that the eigenvalues and eigenfunction depend continuously on the problem. This means that we need to compare the spectrum. And in order to compare these problems, we need to extend the functions Q, P, and R, given by the relations 3.2 and 3.3. We need to introduce a Banach space, given by the relation 3.4, with its natural norm, given by the relation 3.5. We again consider the Sturm-Liouville problem, consisting of the equation 4.1, this time with separated boundary conditions, and with coefficients that satisfy the same properties, only that we need to notice here that P and R are positive almost everywhere on the AB interval. And the main theorem of this subchapter is that if we consider an omega 0 an element of omega, and lambda of omega 0 be an eigenvalue of the Sturm-Liouville problem, then for any positive epsilon, there exists a delta, also positive, such as if omega satisfies the relation 0.45, then there exists an eigenvalue lambda of omega which satisfies 4.6. Starting from the results of Kowalski in the bibliography references 5 and 8, we generalize these results for Sturm-Liouville problems of the form 5.1 with separated boundary conditions. Again, only the notations have been changed. We consider the set D of the solutions of these problems, and also 2 differential operators that are self-adjoint, given by the relation 5.2. Also, for the notations, we use the lambda k for the eigenvalues of the first problem, and tilde lambda k for the second problem. And we obtained the generalization of a theorem given by the theorem 5.1 when we considered the infinite norm of the difference between Q and tilde Q. And if this holds, then the difference between eigenvalues is also less than epsilon. And we also have a corollary that states that if the problem depends on a parameter pair with a Lipschitz constant C, then the difference between the eigenvalues depends on the same on P with the same Lipschitz constant. To simplify the discussion, we assume from now on that L is a positive operator, which means that we have a smallest positive eigenvalue, lambda 1. We denote by F the bounded symmetric operator given here. So we start with again a generalization of a well-known lemma given by lemma 5.1. Under the assumptions above, the following inequality holds. Here we use the inverse operator of L. L was an integral operator, so its differential operator, sorry. So its inverse would be an integral operator that is bounded. The result given by Arcelà-Scoli theorem. And again, the best the best result that we have in this article is that the difference between the error between tilde lambda k and lambda k, the relative error, is bounded by the spectral radius of the inverse of operator L and F. And here we have an example that states that indeed the last approximation was the best. We have a simple differential operator, of course, and we perturb it with the function q. Here is the function q. We have the eigenvalues of the unperturbed operator, and we see here that the best approximation is using the spectral radius. We also have some examples for the results presented above. The graphics are done by me in Python. We consider the harmonic oscillator equation, and here we have the eigenvalues for the initial potential and the perturbed potential. The one with the blue dots are the initial potential, and the one with the red dots are the perturbed potential. We perturb the potential linearly with the factor 0.5. Here again, in Python, the Python numerically calculated the difference between the eigenvalues, and we can observe that in all of the cases, the difference is lower than 0.5, the perturbation that we considered. And also we have the eigenfunctions plotted using Python. It is very important the fact that we use the infinite norm, because if we use the L2 norm, we don't obtain a valid result. Here we have an example of two Sturm-Liouville problems, very simple Sturm-Liouville problems that were the difference between the potential is here. Here we have 0.1 multiplied with t, and here we have 0.1 multiplied with t squared under the same boundary conditions, and we observe here that the norm is way lower than the difference between the eigenvalues. So with the L2 norm, the result doesn't work. And the problem, a more practical problem, we have a string of length L fixed at both ends. We have the function that represents the vertical displacement of this string. This is the equation that we obtained with these boundary conditions. E is the modulus of elasticity of the string material, E is the second moment of area, rho is the density, and lambda are the eigenvalues. And we have here a practical example. We considered a steel string. We got the numbers from the internet, of course, the density, the modulus of area, the elasticity modulus, and everything, and we perturbed the density linearly. So we consider that the density is not constant along the string. Here are the eigenvalues calculated using MATLAB. In the first picture we have the initial problem, in the second we have the problem perturbed with, again, a factor of 0.5. Again, in Python, the difference between eigenvalues that does not exceed 0.5, and the eigenfunctions of the initial and perturbed problem. The graphics were made using Python by me. All of these examples were made using Python and MATLAB codes using that I realized. And here we have the bibliography of this project.
Ok, thank you. Vă mulțumim tare mult.
Mulțumesc și eu pentru atenție.
Da, sigur, mulțumim. Atunci, conform planificării